Hi, my name is Ivan Skrohodov, and in this video I would like to present you hierarchical patch diffusion models for high-resolution video generation, our recent work on video synthesis, which we did together with Willy Menepes, Alexander Serokhin, and Sergey Tulikov. Modern diffusion models are not end-to-end and consist of multiple models and optimization stages. For example, latent diffusion models first train an autoencoder, and then after its training is complete, it trains a downstream diffusion model in its latent space. Cascaded diffusion models first train a low-resolution diffusion model in the pixel space, then the second diffusion model is trained to upsample low-resolution videos. After that, the third diffusion model is being trained for further super-resolution. In this way, existing approaches consist of multiple models and optimization stages, which complicates training and downstream applications, like image or video editing or distillation. In our work, we develop HPDM, a hierarchical patch diffusion model for high-resolution video synthesis. During the optimization stage, we sample a random video or image from the dataset and crop multiple patches of various scale but the same pixel resolution. And then we feed them into the joint diffusion model to denoise all of them jointly. In this way, we have just a single optimization stage, making the overall method completely end-to-end. During inference, we first generate a low-resolution patch from a low-resolution noise map. Then we initialize a high-resolution noise map and tile it to the corresponding patch resolution. Using the previously generated patch as a context conditioning signal, we generate the upsampled version of the video. Then we repeat the procedure until the desired target resolution is reached. Here is the detailed architecture of our model. Given a high-resolution image or video, we randomly extract patches of multiple scales in such a way that they are located one inside another. Then we tokenize each patch with a VAT-like procedure. This procedure looks the following way. We patchify an image into small crops of the same size. In practice, we use 4x4 pixels. Then we flatten them into a 1D sequence and project with a linear layer. The obtained representations serve as a 1D video embedded sequence. After that, we process them with 6 ring-based linear attention blocks. Each ring-based block has the following structure. Latent tokens, initialized from learnable embeddings or provided via a skip connection from the previous block, read information from the data tokens through a read cross-attention layer. Then, 4 self-attention layers are applied to process the latents, and the result is written back to the data tokens through another write cross-attention layer and returned from the block. After the ring blocks, we detokenize the data sequence. It is a symmetric operation to tokenization and looks the following way. We take the data tokens and project them back to the pixel space. Then we unflatten them to obtain the proper video shape. Similar processing is being applied to patches of higher scales, but with two differences. First, we use adaptive computation. We skip some ring blocks for higher stages of the hierarchy to save computation and memory, and because modeling high-resolution texture details is typically easier. Next, we develop context fusion, providing the global information to higher resolution stages. It is structured the following way. First, we take the activations of a given high-resolution patch. Then, we compute the coordinates of this patch inside all the patches from the lower stages of the hierarchy. After that, we grid sample the features using trilinear interpolation, average them out, and project via a linear layer. We perform two main lines of experimentation. First, we benchmark HPDM for 64 frames long 256x256 class-conditional video generation on UCF, which is the most common video synthesis academic benchmark. Our model achieves state-of-the-art quantitative results, outperforming even a fine-tuned version of Make a Video, which was pre-trained on a large-scale dataset. Qualitatively, HPDM is able to capture complex realistic motion and semantic structure, which is evident from observing even its completely random samples. Another interesting line of experimentation we conduct is fine-tuning a low-resolution video generator for high-resolution synthesis. For this, we take Snap Video, which was trained for just 36x64, 60 frames long text-to-video generation, and train the model for 15K steps with our hierarchical patch-wise strategy for 288x512, 64 frames long video generation. Even such short fine-tuning allows to obtain comparable high-resolution synthesis results. Our work is a step towards end-to-end training of high-resolution video generators. The key findings which we deliver are the following. First, patch-wise generation turned out to be a viable strategy for high-resolution video synthesis, even though it is often neglected by the community. Second, our work demonstrates that natural videos contain a lot of redundant information. HPDM can be efficiently trained when using even 1.5% of the original pixel values. HPDM allows rapid fine-tuning from a low-resolution generator, which hints that a low-resolution model already knows high-resolution synthesis and needs to be just nudged towards it. And finally, end-to-end high-resolution video generators would be very useful to the community and would allow to simplify both training and many downstream applications.